Hello, everyone. Thank you for coming. While we are waiting potentially for some people to come in, I'll tell you about what we are dealing with here. So this is a webinar about parsing, about C++. Um, I will be showing you slides and telling you stuff. And if you have any questions, please write them down in the chat. When we get to the last slide, to the finish, I will look at the chart and I will read your questions you might have and I will answer them. Okay, so please stay muted. I know we are muting everyone, but do not give in to temptation to talk because it will cause chaos. So thank you again for coming. Let's begin. Okay, so who am I to speak here, right? My name is Yuri. I work at PVS-Studio for about 6 years, and I'm working on the C++ static code analyzer. And my main focus is working on the part which actually deals with the language and with parsing, semantics, and stuff like that. So basically, if you don't know, a static analyzer it's like a compiler light version because it doesn't generate code. It just acts as a front end for a compiler, and then when it parses your input code, it will give you a report on any errors or irregularities or something wrong in your code it finds, basically. Okay, so we are talking about parsing. So what is it about? What is parsing? Let's look at some input like this. How it goes, we take a string, a huge string, usually it's a source file or something, as input. And then this string goes through the lexer. Lexer is a small, actually simple piece of code which tokenizes your input. So what it does, it divides the entire source to some small pieces and it labels them. So as a result of, in this example, as a result of lexing, we get something like that. So ID equals sign ID, blah, 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 etc., etc. And this token stream, so-called, it goes to the parser then. And actually, the parser, its task is to take some input and tell you whether it belongs to the target language or if it doesn't belong to the target language. But obviously, this thing is kind of useless. I mean, how often do you have to check if you get something in some language just for the sake of checking that? So usually it's used for something different. If we look at this expression here, we can actually rewrite it and structure it a little bit differently as a tree. And the parsers in compilers and interpreters and stuff like that, they usually produce ASTs. Well, this actually, what you see here is an AST already, but let's make it more like real world. It would look like that. So meaningful nodes with some meaningful information minus punctuation, parentheses, and stuff like that. We collect from code what we need to do, what we need to collect to understand what's actually is going on there. How do we know how to build this kind of AST? Well, we have grammars for that. And in any language, in a programming language, in natural language, everywhere, we are dealing with grammars. In natural languages, usually we just ignore that. We kind of understand them intuitively. So we don't necessarily need to know theory behind it to understand what is spoken, right? But for a machine to know, we need to formalize it somehow. Well, speaking of natural languages, if you look at this string right here, it also does have some grammatic features. So English follows this structure, subject, verb, object, usually. If we highlight them, the articles are kind of semantic information. They do not interest us here, but if we look at this sentence from the point of view, like how a compiler would deal with it, we would get something like that. So it looks like a binary expression, really. The verb is like an operator, and subject and object, the one who acts and the one who is being acted upon, are like operands of that operation. All right, so grammars can be different. And they usually are there are different types of grammars. Grammars of kind of a lower order are like regular grammars for regular expressions, and there are higher order grammars which incorporate those lower order grammars as just one case. Like the regular is the simplest. Context-free is what usually all programming languages we know deal with. Context-free grammars, they incorporate kind of as a subset regular grammars. Also, we have context-sensitive grammars. It's like a back language, for example, when you're dealing with strings where every letter repeats for the same amount of times. Like every time, if you have an A, you will have this. If you have one A in one word, you will have one A in other words, and so on. And it so happens that the more complex the grammar is, the more higher order it is, the easier it is to use it for humans. So it's kind of like if you try dealing with regular expressions, you know how difficult they can be to understand and write. But in natural languages, which are the higher order of things possible, we can speak naturally and easy. And for computers, it's the opposite. The simpler the grammar, the easier it is for a computer to understand, and the harder it is for a human to use. All right, let's look at those things more closely. And for that, I'm going to invent a language. It's going to be a small and actually silly language, which will just have one type of expressions. But let's see how grammars are written first. They consist of things called productions, and there are non-terminal and terminal productions. So this expression list here is a production, and it's a non-terminal one. How do we know? Because an expression list consists of expressions, and also it can be an expression list to which we attach an expression at the end. This grammar is written recursively, and that's a good thing and a bad thing at the same time, but we'll see later. Okay, so expression in our example can be a binary expression. We only have one kind of expressions, binary. Binary expression is, again, it can be an ID, and it can also be a chained binary expression. So we can have a binary expression consisting of multiple operators in a row, like 1 + 2 + 3 + 4, for example. And as the operator, we will use this $, which we actually don't care what to use here, but for the sake of example, that's going to be a $. And here, ID expression is a terminal one. It does not depend on other productions. And that's how we know it's a terminal production. And it can be either A, B, C, or D. Just literally one of those letters is an ID expression in our language. So just to give you some examples, this is a valid expression or sentence in our language. This is also a valid sentence, this and this. And any combinations of those will be two valid. And let's see how parsing would occur on that. When it comes to parsing, there are two big categories of parsers which we can apply, and the category they fall into depends on how they traverse those grammatic productions. We have descending parsers. When you start at the very top, at the root, in our case, it would be expression list, and you go down to the very bottom, you find something valid here, there, you climb up and you apply productions and grammar rules as you go up. And ascending parsers work in a different way. They usually consume some piece of your input and they try to figure out what it is. And then as they collect and accumulate more and more pieces of input, they can then make a conclusion of what they're dealing with. We'll look at both right now. So here's our expression we are going to parse. Let's try to parse it first with the descending approach. And by the way, this descending parsing is a very popular approach and everyone seems to be using it. And there's a reason for that, because that's the only thing you can actually write manually. An ascending parser, you would need tables and state machines for. So you can't just, describe it in code. You have to use a lot of data, usually pre-generated data. If you're familiar with something like Python or whatever, they usually do that. You describe grammar to them and they generate a huge state machine for you. Okay, but right now we are using recursive descent. How does it work? Imagine a class called parser somewhere, and it has functions in it. And the first thing we do is call the expression list function, because that is our root production in our grammar. From expression list, we go to expression, we go to binary, we go to ID. In ID expression, we find and consume that, hey, we've got A. That's a valid ID expression, so we take it. All right. And we stash it somewhere and go up to the binary expression from which we came to that ID, the left operand. Then in binary, we look at the operator, say, hey, that's our operator, let's go parse further. And then we bump into B. That's again ID expression. And we kind of wrap them both A and B in a single binary node as operands. Okay, so the second one goes exactly through the same chain of calls. We consume C, and we get this. If you remember the example I showed you, like when we started, there was an assign expression and the tree was growing to the right there. And here it's growing to the left. Why is it growing to the left? Because we have operation associativity. Binary expressions like arithmetic expressions are left associative. They grow to the left if you have a chain of the same operators. And things like assign, they grow to the right because they are right associative. And the order in which we build the tree of our expressions, it determines in which order they will be evaluated when we get to that. So in binary, we always have to evaluate the expression left to right. We cannot do it in a different order. Okay, and if we wrote code for that, it would look something like this. So let's say we have a method in our parser called binary export. So here we get a left operand of that binary expression ID. Right now, we just return it, but obviously it's not what we want, so we have to do something like that. The loop here is needed to deal with, again, chained operators of the same kind. That's how we can parse successfully A, $B, $C, $D. And okay, if you look at this, if you are observant, you can notice that here we call ID expression twice. And the question arises, what's that? Why aren't we using it, right? The binary expression is never called. And that is because our grammar is written recursively. So binary expression is defined via itself. And if we called binary from binary, we could easily cycle infinitely and eventually probably crash because that's a recursive chain of calls. To avoid that, we kind of a little bit unwrap the grammar, and we do not use productions inside productions. We take the first sub-production from that target production and use that. In this case, binary consists of an ID. That's the first thing you can check in a binary production. So we just, that second binary highlighted in red, we turn it into ID expression to avoid recursion. Because in recursive descent, rule number one is that you cannot have left recursion in your grammar. Funny enough, we use the grammar defined recursively, but recursive descent cannot deal with grammars which contain left recursion. And we can deal with it just because we a little bit massage it into the algorithm so it fits. That was recursive descent. Let's see how an ascending parser would deal with that. Again, same expression. Here's our simplified grammar. I won't be showing the entire thing from expression list further down, but keep in mind that those productions are still present. I'm just going to show you on the example of a binary. So what we do, we move our lexer left to right, and we consume tokens from the input. The first token will be A. And by the way, here we have some memory. That's a state of the state machine, which is an ascending parser. So consume A, put it into the memory, and we'll look at it. What could A be? And if we look at our grammar, A is an ID expression, right? Because we have a production called ID expression where we have A. Okay, now we have ID expression in our state and an operator in our input. So we look at the input and we have to decide what to do next. And we can do two things in an ascending parser. We can shift. That's what we are doing when we consume something from the input and put it into our state. And we can reduce. When we take our state and everything written there and we turn it into something else, into a production of a higher order of priority, a more common, a more parent production. In this case, we have ID expression and we have an operator in the input, and we don't have nothing which tells us what to do with it. But we have in binary, we have that production binary expression, operator, ID expression. And binary is also itself an ID expression. So here we reduce. We do not take another character or token from input. We turn our state into something else. So now we reduce our ID expression into a binary expression. This is a logical thing to do. Of course, we do not create a node in our AST which says it's a binary, but it's actually not a binary. This is a state. This is a label we have in our state. Okay, so now we can deal with a binary expression and operator. So we shift our operator to the state. We cannot reduce anything. Cannot reduce this state into anything. So we decide to shift again. And we take another ID expression, put it to the state. And now, according to this grammar rule, we can reduce binary operator ID into another binary. And we just repeat the same thing, again binary, again ID, and again binary expression. So that's how ascending parser would work and deal with that problem. Okay, so now you're probably like this. We are talking about C++. Where's C++, right? Well, let's look at C++. It also has grammar, which is enormously huge. And if you want to create a parser for a language, you probably want to start where it's easier. And the easiest thing to start, usually expressions, because they are straightforward, at least. So let's look at expressions. That was our made-up language. And if we look at an actual thing which could happen in a C++ parser, it looks kind of like this, exactly the same. So here we are looking at an additive expression. As you can see, it can contain multiplicative expressions and operators plus or minus. And again, it's written this way because operation priority. If we go like this, we call mul expr first, and then we call mul expr in a loop as the right-hand side operand. If we have a mixture of multiplications or divisions and additions and subtractions, we naturally, without doing any tricky logic, will get the correct tree where multiplications and divisions will be operands of additions and subtractions. And when we try to calculate the entire expression, we go bottom up and we calculate multiplications and divisions first and additions and subtractions last. That's kind of an easy case, but turns out that expressions in C++ are not that simple. Because we have lambdas, and this one won't compile because our lambda does not return anything, and we don't even know what type it's supposed to return. So let's explore it, shall we? Let's see what a lambda can contain. Well, it can contain, for example, structures. Structures can contain functions. Lambdas can contain also lambdas. You can declare variables. You can use arbitrary statements and call constructors and functions and stuff like that. So if we want to parse expressions in C++, honestly parse them without cheating and stuff like that, we have to actually parse the entire language. Because if you look at the primary expression, which is the lowest possible type of expression, it's like literals and IDs and stuff like that, you have lambda here. So it's the most basic expression is a lambda. Well, one of the most basic expressions is a lambda. And in lambda, you have things like compound statements, declarators, and a lot of stuff beside that. And compound statements are, those curly braced bodies, which can contain statements, and statements can be declaration statements. So if we want to parse expressions in C++, we have to deal with declarators and declarations. Okay. What can go wrong, right? I think nothing can go wrong, except if you look at these, one of them is a function, and the second one is a variable with an initializer. I don't know why you can use parentheses to initialize things. I personally don't like that. I think it would be better for all of us if we were not allowed to use them. But okay, it's in the grammar, we have to deal with it. So let's go and deal with it. I'll start with the variable. You'll see why. Okay, recursive descent. We are going left to right and deep into the grammar. The dot here is where we are currently standing at. So we start right before int. Okay, let's go. We want to parse a declaration. Declaration can be a name declaration. It can be a block declaration. Which can be a simple declaration. And by the way, that's a trigger. Because in C++ grammar, if you see something labeled simple, be sure that it's anything but simple. We'll see in a moment. Okay. Declaration specified sequence next. we haven't moved our position yet. And when we go into the declaration specifier sequence, through more steps down, we eventually consume int. So that's our declaration specifier sequence, a single int. It's a type specifier. Again, it's a simple type specifier, which is not simple grammatically. All right. Now, next we have an init declarator list, which is an optional production. So in a declaration, we can have just the type name and a semicolon. So that's a valid declaration. Int semicolon is a valid declaration. It doesn't declare anything, but grammatically it's correct. Glenn, by the way, will tell you that it doesn't declare anything. Okay. Init declarator list consists of an init declarator. And remember our expression list, which can have an arbitrary number of expressions separated in commas. The same things here. You can have an arbitrary number of declarators separated with commas in a declarator list. Okay, so we go into declarator. We go into a no PTR declarator. Why don't we go into a PTR declarator? Because for us to go there, we have to see either a pointer or a reference declaration. So if we don't have an asterisk or an ampersand, we just go out of the PTR declaration production. It doesn't interest us. Go to no PTR. Eventually, again, through a long call chain, we get to the declarator name, unqualified ID meow right now. So we consume it. And next, we are dealing with parameters and qualifiers list. Okay, let's go. What is parameters and qualifiers? It's something in parentheses, which is fine. It's easy. And here we have this parameter declaration clause. What we get here is BAM. Why? Because we have two in parentheses. Two is not a type name. It's not a qualifier or anything like that. It's not a declaration. So we cannot parse a parameter declaration at this point. It's a syntax error. So how did we get there? Let's see. Again, our function and our variable look very similar, don't they? So for a function, we can present grammar for it like that. And for a variable like that. And if you look closely here, you will see the problem. We have two things in a language which start the same. And if you look at them like we are looking in the recursive descent, if you look at them left to right, you cannot tell which one of them you're looking at. And this brings us the second rule, the thing that recursive descent should not be dealing with. You cannot have prefaces which overlap in two different productions. And as you can see, we are violating both. We are violating left recursion and the overlapping prefix thing. And it's a problem so prevalent in C++ that it has its own Wikipedia page. It's called most vexing parse. look at that. So let's say we have two structures. One is just an empty thing, and the second one is also empty, but it has a variadic constructor. So it can take an arbitrary number of expressions as arguments. And we have two declarations like that. If you want to guess, I'll look at the chat for, I don't know, a couple of minutes. If you want to guess what these are, you can write your guesses in the chat. If you don't want to guess, I'll just wait a minute or so and continue. Well, in this case, maybe it's kind of obvious, but okay. Let's continue, man. I'll give you an answer. These are function declarations, both. The first one is a function which returns a cat structure and takes by copy an object of type of those structure. And the second one also returns cat, but it takes as its parameter a function which returns pause and has no parameters. And if we look at that, which is actually really similar to the previous one, suddenly it becomes a variable. Why does it become a variable? Because inside our parentheses after the name, we have another pair of parentheses which makes whatever is written there an expression, because a paren expression is one of the things which count as a primary expression in C++. And yeah, it's a variable initialized by an object of the pause type. And it gets even funnier and funnier, because these two are suffering from the same thing. The first one is a function declaration with 4 parameters which are also functions. And the second one is a variable declaration which is initialized by objects created by calling their respective constructors. And what makes them different? What makes them different, we'll see in a moment. And here we are dealing with a bit of a problem, because this part is ambiguous. You do not know which exact dramatic production you are dealing with if you just look at this first part. And to understand that, to understand which one, is it a function or a variable, we have to go all the way back there. Because this last part, which makes the difference, whether or not we have a function or a variable. Well, but somehow all compilers, well, at least all major compilers like Clang or GCC, they all use recursive descent and they somehow deal with it, right? So how do they deal with this situation? Grammatically, it seems like nonsense, and recursive descent should not be able to do it. Well, usually what everyone does is backtracking. For every restriction, we have an asterisk, kind of, which says that, yeah, you cannot do that, but you kind of can. What we are going to do now is when we get a syntax error in that production, when we were parsing the variable, we will go back. So let's see how it goes. So as you remember, we are here and we get an error here, right? Instead of just saying, oh, it's an error, I give up, we go back. We have a declarator here. We don't have parameters and qualifiers, and we don't care at this point because we'll go and try to see if it has an optional initializer after that. So int meow in our case is a declarator, and now we are looking if it has an initializer. Okay, let's go into initializer. Trace or equal doesn't work for us because it should have curly braces or an equal sign, so it goes straight to expression list in parentheses. We go consume the parentheses first, and then 2 is an expression, and expression is an expression list because the grammar is written this way. Okay, so with the use of a simple backtrack like step back, we can deal with every problem in the world, including most vexing parse. Easy. Right? Well, no. Restrictions have asterisks, and things under asterisks have double asterisks that say that we cannot do it safely. We cannot but just do backtracking every time. Why? Because in most cases, in simplest cases, backtracks are fine. You can just go, get something you do not expect, go back and try a different path through the grammar. But in some cases, backtracks can lead to exponential complexity of your code of parsing. And recursive descent, a nice thing about recursive descent is it is guaranteed to work for linear time. It has linear time complexity, but here we are breaking that guarantee effectively with backtrack. Okay, how can it bite us? Let's see. There's this funny example. When you have some template class which accepts 2 parameters, it accepts a size of, well, memory pool and the type of the element stored in that memory pool. And what you can do with it is something like this. So you declare a pool of memory pools and so on and so forth, increasing this amount of elements as you go down. The last one here is just an empty structure, but it can be something more useful. This example is for demonstration, so it doesn't really matter what to put there. And just to be able to see it a little bit better, let's do it like this. And let's see what happens when we try to parse it with backtracks. Okay, here's our grammar. We are in type def. And we need a simple type specifier. And as you can see, again, this word simple, which is not simple, and usually it is where problems occur. So we're here. To parse a simple type specifier, we need to parse a nested name specifier first. And it's an optional production, but we still have to try. Okay. What is a nested name specifier? It's a type name, namespace name, or a template ID. I will skip type name and namespace name. The real parser would probably go and check whether it's one of those, but for the sake of this demo, let's just skip them. Let's just believe that we are parsing a simple template ID. Okay. How do we parse a simple template ID? Well, it's a name of a class and then template arguments. We consume 16 here, no problem at all. And we, like the first template argument is okay. And the second one is, again, a simple type specifier, which we do the same thing with. We go to nested name and so on and so forth. And eventually we go all the way down here. And yeah, that's fine. We are looking at a simple template ID. Good. So we can parse it. But remember, we are inside the nested name production. And what happens is we parse a simple template ID, but the nested name specifier requires 2 colons at the end. And we don't have those. So it's a backtrack because we have a template ID, but we do not meet the criteria for nested name. Okay, let's go back. Go back here. Again, I'm skipping some stuff which is irrelevant right now for us. Eventually, we will bump into this thing, and we parse that piece as a simple template ID. Good. Now we can go back our call stack to the parent expression, and then we since we've returned the first template argument, the second template argument, we know the template name, we can parse this MP1024 as a simple template ID inside the nested name. So again, we don't see those 2 colons, we go back. Here we say, all right, so we went back, let's go down and try a different path. And try the path the same we used the last time when we don't have a nested name specifier and we just have a simple template ID. And we go all the way down here again. But here we backtrack again. So what happens is you go all the way back. You decide, hey, I need to backtrack. You backtrack, try a different thing. You parse that piece down there successfully. You go back up to the previous template declaration instance you were called from. You say, hey, I have 2 arguments. One of them is a number, the other is simple template ID, but I don't have the 2 colons, so I have to backtrack, and you backtrack again, and you go all the way down again and backtrack on every step up, and so you end up going in circles over and over, doing the same thing, parsing the same kind of sequence of tokens almost infinitely, because it's an exponential complexity. So every time you go down from any point of this, I don't know, what do you call it, a hierarchy of instances, from every point you start, you will do many passes through the entire subtree of that expression. And that's not good. I feel like that when I look at it for some reason. In this exact example I've just shown you, we did some measures, and it turns out that about 10 levels of enveloping can complete in some reasonable amount of time. But if you go past that, you may try to parse that thing for hours, or maybe even never finish it. Okay, so how do we deal with that situation? Remember, first problem we had is left recursion. It was easy to deal with. We just unwrapped the grammar. And with this, we have to deal in a different way. And if we can do it, we can recursively, we can apply recursive descent to a C++ grammar, no problem. Okay. Here's our made-up language again. Let's add a disturbance here. In expression, we have a binary export right now. We'll add another one. Let's call it a joker. And the joker looks like that. So it's a binary expression, operator, and X. Capital X, exactly. Okay. Now we have, in addition to what we already have as valid expressions in our language, we also have stuff like that or that. Different combinations where you have some expression, operator, and capital X. And here's the situation we are trying to deal with. Two productions in our grammar start the same. So it violates the second rule of the recursive descent, where prefixes cannot overlap. Let's see how do we deal with it, preferably in linear time. Okay, let's take this expression and parse it. And we also will be tracking the current position we are in, the current lexer kind of point of view. We start at 0 because we start always at index 0 at the very left. And again, we go through the call chain to consume A. And then we consume B, and eventually we build the binary expression right the same way we did at the very start. Lexer position is now 3 because 0, 1, 2, and we are currently positioned before the second dollar sign in this. And we will do something related to the ascending parser in this case. We will take part of an ascending kind of approach, and we'll have a state. We do it for every production we come across naturally, but again, here we have a binary expression, and I will show you just how it works with the binary. So we've built a $B binary expression. We don't want to ever do it again because we already have a valid expression. We know it's valid. It's a piece of a bigger one, but it's okay. And we already also have an AST node for that. So we stash it in our state along with the lexer position, and that's the position after the expression. So again, like our binary is 3 characters long, 3 tokens long, and the position is 3, therefore. Okay. And then we consume that. By the way, we are still in that loop in the binary expression I showed you. So we consume the dollar sign, so far so good, and then we have a problem because a binary expression doesn't know what to do with the capital X. It only wants an ID as its right operand. So what we do, we backtrack to the very beginning, but we keep our state intact. Whenever backtracking occurs, we keep whatever's on the state in the state it was before backtracking. So now, since we backtracked, we know that the binary expression production failed. It decided to go back and report that, hey, I'm seeing some X there. I don't know what it means. And that's how we know in our expression production that we have to go a different route. And different route, since expression is either binary or a joker, we go to joker, and joker eventually calls binary. And here is the good part of it. Since we have that state, and since we have already parsed first part of the entire expression as binary, and we know it's binary, we know it's valid, we do not actually go and parse it again. We just take it from the state, and this one, we just take it from the state, we take the entire AST, the part of AST built for it, and we just move our lexer to the correct position. So we have kind of parsed the binary part again, but we didn't actually parse it again. So we parsed it once and it was stored, and now we are using it. Okay, so we move then our position, and here we see X. That's just what the joker expects. And we are successfully in linear time have parsed that expression. If we didn't have that, that stashing thing, we would go again through the motions of doing A and then dollar and then B and so on and so forth. And probably we would backtrack again and have to deal with it somehow. So it would have taken more steps to do. So back to our example. All right. How can we deal with that painlessly, kind of? Well, again, we go all the way down, and again, at some point, we successfully parse the simple template ID here. But we still have to backtrack because we are in the nested name specifier production, which expects 2 colons at the end, which we don't have. But now, instead of just, backtracking mindlessly, we will say that, okay, here we have a simple template ID. We will stash it. And the same happens on every step. We go inside, let's say inside that piece of code here that the arrow is pointing at. We go inside it, we see, hey, it's a number. Okay, we have a number. And then we need a simple type specifier, which is a simple template ID. And we go like, hey, we already have that. And we never go into nested templates again, ever. We just visit every one of them once, exactly. So it continues back, back, back. Eventually we go here. If we, again, when we go through that entire template ID, like to the closing triangle bracket, we will backtrack because it's not a nest name, but we will have parsed the simple template ID successfully. So we backtrack, we go forward again, we see, hey, we already have that thing parsed. So we consume it just from our state without the need of going through it again. So that's how you deal with the second limitation of the recursive descent. You just keep track of what successfully parsed pieces you have available for you. And here, actually, that's all from me. Now, if you're actually, I'm going to do, I think, a couple more webinars of different topics regarding C++ parsing. This one was about parsing. The next one will be about semantics, and the third one will be probably about types or evaluations. If you want to keep in touch and stay tuned, here's the QR code which leads to our Twitter or X page, where we will be announcing the upcoming events, so you can be sure you don't miss them. So I hope you liked that. I hope you learned something, and I'm glad to answer any questions if you have any. So thank you.